Okay, off we go. Time to get started. So real quick before we get into the math, let me just remind everybody, I sent the broadcast email out Friday, I think it was. Today is our first day of checking attendance. So per the email that I sent on Friday, there on the board is the 5-digit number that is the answer to the only question on the quiz named by today's date. So if you go into the Canvas site, I hope and presume y'all all have the Canvas app on your phone. It should be pretty self-evident. Look for today's date on the list of quizzes. Take the quiz. That's the answer. Type it in. Make sure you got the credit. Right? You do have to confirm. It's your responsibility to confirm that you are credited with the correct answer to the quiz, and then you're good. You are checked in as present for class. Okay. So more details, of course, in the email that I sent. Make sure that you're thoroughly comfortable and aware of all those details. Okay. So picking up where we left off, we were talking about linear approximations. In fact, let me rewind just a little bit and hit some highlights. This is the big idea of a single variable linear approximation. Right? This function is the only degree 1 polynomial that agrees with f in both value and derivative at the point A where we're basing the linear approximation. Okay, so with that in mind, here, let's see, wait a second. Here is the formula for the linear approximation of multivariable function, real valued multivariable function, and this too has those same properties. This is the unique degree 1 polynomial that agrees with f in value and all of the partial derivatives. So this is sort of the moral equivalent of the single variable formula. Okay, all right. Now that said, there is a limitation on what we just did here. You'll notice now that this is for real valued, right? Single output variable. So the output value of this function is just a real number. So the next thing we're going to do is we're going to entertain the possibility of what if you have more than one output variable? What if you have several output variables? What if you have a vector valued, that is, multivariable function, and can you write down a formula for the linear approximation of that? Now, real quick, I'm going to take another quick pause. Some of y'all came in after my reminder to the email that I sent out on Friday. Don't forget to take the attendance quiz. In general, just be advised, the attendance quiz will disappear 2 minutes after the scheduled start time of class. That is by design. The idea is that being on time for class is a requirement, and if you're not on time, then you're not really following the rules. So do make sure that you're on time, and then do make sure that you can get that code entered into the Canvas site before 2 minutes after the scheduled start time of 10:20. Today it's extended. Today I'm giving 10 minutes, just kind of first day. Just want to make sure everything's glass smooth. Going forward, 2 minutes after the scheduled class time. Okay, so multivariable vector valued function, and here's the answer. And you'll notice again, it looks a lot like the answer that we saw on the previous page, which looked a lot like the single variable answer. And this function has the same features. It agrees with f in value and in all of the partial derivatives. Do notice that when we say all, we mean with respect to all of the different input variables. And furthermore, partial derivatives of all of the now several different output variables. So that's a lot of partial derivatives. Right? So this function is the function that will behave as such. So now, what is this df thing? Let me clean up my mess here. What is this df thing? This df is a matrix. Right? This df matrix is the magic matrix that makes it work. Right? This was crafted explicitly to make that linear approximation formula work correctly. In the same way that what we call the gradient vector here was crafted, right, to make this formula work. Right? So this is a clever definition, I guess you might say. Okay. Alrighty. So anyway, now let's pay a little bit of attention to the details of how this matrix is constructed. Notice that in the first column, all of the partials are with respect to x1. So column number 1, all of the partials with respect to input variable number 1. Likewise for the other columns. So one way to think about this, the way I like to think about this, is that columns correspond to input variables. Which input variable are you taking the partial with respect to? Now likewise, let's look at the rows. Let's see here. In this first row, notice that we're taking a partial of f1. All the partials in that row are partials of f1. In other words, the row corresponds to which output variable you're taking the partial derivative of. Okay, so columns correspond to input variables, rows correspond to output variables. And that's something you just have to remember. It is very, very important that you get it in the correct, if you accidentally get that wrong, you're effectively transposing the matrix, right? And that's not the same matrix, and then everything crashes and burns. Does that make sense to everybody? Okay, so I think this is another nice exercise to confirm that this works. In other words, take this formula for that matrix, look at this function, and explicitly confirm that these properties hold in exactly morally the same way that you did for the single variable version. Right? Remember we talked about that this is something you should make sure that you're able to do. Do be advised, reminded, that this derivative here, because it's evaluated at the fixed point A, that is now a constant and should be treated as a constant when you're taking the derivative of L. Right? So that's a little trick that's a landmine to make sure not to step on. And then likewise here, analogously, this, notice, evaluated at A, right? And so this is and should be treated as a constant as you take the various derivatives of the function L. Okay. So again, great exercise. Give that a shot. Make sure you can confirm that these properties hold. Okay, and then a quick example. Now again, this is very plug and chug, right? It's a lot like the plug and chug question that we did here. Let's see here. We had this function, and we just explicitly cranked it out by evaluating the appropriate derivatives and plugging in the appropriate givens in the appropriate places. So same thing here. This now, let's see if I can, it doesn't quite all fit, but this is the formula that we're going, there it is, that we're going to plug into here. And it's just a matter of, again, cranking out the details. Now part of this is easy. The value of f at A, well, there's f, there's A, plug it in, nothing to it. What about the next part, df at A? Well, first we're going to have to compute df. First we're going to have to take the various partial derivatives of f. And then we're going to have to assemble those various partial derivatives in the exactly prescribed way, right? Again, that's important. Make sure you get that in the prescribed way. Inputs correspond to columns. Outputs correspond to rows, etc. Then we're supposed to plug in the point A. Okay, so I plug that in, and out comes then what is the evaluated derivative matrix there. Everybody on board? Okay. All righty. Okay, moving along. Couple of little quick observations. These are just kind of cool, useful here and there. But we've already noted that the columns correspond to input variables in the sense that each column is full of a bunch of partial derivatives of coordinate outputs with respect to one, specific corresponding input variable, right? So all the partials with respect to that one input variable. But we've addressed this as a statement about individual partial derivatives of individual output coordinates. Here I'm making the slightly different statement that you can think of the entire column all at once as being the partial of the entire vector-valued function f. Vector-valued function, it's the partial derivative of that thing all at once with respect to x1. That's a slightly different statement. The distinction ends up being something that we don't really need to. It's some details that are ultimately not deep points, right? So I'm not going to get into the weeds on exactly why that's true. It's just a bunch of little micro details, and it's not hard. And it's something that y'all could do yourselves if you're interested in. It's not deep, right? But anyway, just going to make that observation that the columns are partial derivatives. And then here's another observation, and this one is a little bit easier to just kind of notice. The rows are gradients. The rows are gradients of specifically individual output coordinate functions. And easy to notice. I mean, let's remind ourselves, what is the definition of a gradient? A gradient is a gradient of a given function, in this case f1. A gradient is the vector whose coordinates are, well, all of the individual partial derivatives of that function. And that's exactly what that first row is. So the rows of a derivative matrix are gradients. Now, minor little detail, technically gradients are vectors, and vectors we write as columns. This is a row of a matrix, so technically a little bit different, but in terms of, but what are the numbers that define these things? Yeah, they're exactly the same. All righty. Okay. Another little fussy little detail. This kind of thing has bugged me in the past, but it used to really bother me that this thing called a linear approximation is actually not linear. Right? If you think about it, a linear function, a linear transformation, technically has the feature that, by the definition of the properties it has to satisfy, you put in 0, you get out 0. All linear transformations have this property, right? 0 in, 0 out. That formula clearly does not have that property, right? So, unfortunate terminology, linear approximations are not linear. Now, they are this they're called affine. Affine is basically just a recognition of, okay, well, yeah, but come on. Clearly what we meant is, the graph is a line, right? So that brings up the question of why do we call these linear approximations? And here's, roughly speaking, the answer. The answer is because the heavy lifting of the linear approximation is being done by a matrix. That's what's doing the bulk of the work, right? And the matrix is linear. So what we call the linear approximation is something that is fundamentally based on an object that is linear. And so it's a little bit of an abuse of terminology, but what are you going to do? So, true fact. Everybody all right? Okay. All righty. Okay, so another little point of fussiness. But again, this is kind of fussiness I think is really important. We spent some time talking about the difference between a function versus the graph of the function versus the level sets of the function versus that function as a parameterization, right? There's a bunch of closely related but different, importantly different things. And we have to be fussy about these things because the calculus of graphs is not the same as the calculus of level sets, blah, blah, blah. Okay. All right. So along those lines, no pun intended, there is a common conflation that we, again, need to be careful about. Very often, the linear approximation is conflated with the tangent line. And you got to be more careful than that. It's importantly not true. The tangent line is the graph. It's the graph of the linear approximation, right? So the tangent line is closely related to the linear approximation, but one of them is a function. The linear approximation is a function. The tangent line is the graph of that function. It is one of several possible different ways conceivably that you could try to visualize that function in some sense, but it is not the same thing as the function. Okay, so a little fussy, but there it is. So in perfect analogy, let's think about what happens if you have two variables. Well, again, we have a linear approximation. There's our linear approximation. Notice it's a function. It's not a picture. It's an algebraic object, right? And then likewise, we can talk about, well, yeah, but what is the graph of that function? And that graph of that function is what we call the tangent plane. Now, why do we call it the tangent plane? Well, if you look at that formula and keep in mind that this is a constant, and furthermore, that is a constant. Right? A little bit easier to see that this function is actually a pretty simple looking formula and not hard to sort of dot it out and move terms around and find you will literally get the equation of a plane. And so we call it the tangent plane because that is what it is. That graph is literally a plane. Okay, so again, don't make the mistake of conflating the linear approximation function with its graph, that is the tangent plane. All right. Okay, so moving along. Yeah, this next several pages is, I'm going to kind of sort of say we're going to skip it. I leave it in here because this is really cool ideas. And if this were a year-long course instead of a semester-long course, I would probably spend 3 days talking about the subtleties and the beautiful distinctions and clever arguments and really powerful, I think, lovely mathematical ideas around the idea of differentiability. But it is subtle, and we've got a different goal in this course. And this is very sort of math major kind of stuff, very pure mathematician kind of stuff, and not really, Math219, we need to get to computations and stuff we can actually do things with in a practical sense. And so in that sense, this doesn't really quite fit. So it is optional. I do want you to know what it at least addresses. So I'm going to go back a few pages and remind you that when we started talking about linear approximations, I had to put a little disclaimer here. And the disclaimer here is if the linear approximation exists, some functions, you can't talk about the derivative. Or some functions might be weird enough in some way that this formula mysteriously doesn't work out as, what we would reasonably want to call a linear approximation. What this collection of pages, there's 2 pages here of notes, what this addresses is, okay, what could go wrong? How could it go wrong? How can we tell in advance that something's about to go wrong, right, and avoid those situations? And I'm just going to skip to the punchline. Again, it's a very cool analysis, and here is the punchline. The definition of differentiability, roughly speaking, a function is differentiable if the formula that we wrote down previously is, reasonably could and should be called a linear approximation. And the test of that is that we need this expression called relative error to approach 0 as you approach that base point. And this is what we call vanishing relative error. Now, why that is the expression, again, is something I wish we had time for. We don't, so don't worry about that part. Anyway, just do be aware that there is such a definition. Be aware that this definition of differentiability is hard to work with. Among other problems, it involves a multivariable limit. Y'all may have already noticed that we just kind of leapfrogged right over section 2.2 in the textbook about multivariable limits. So we don't really quite have the tools to even really be able to formally recognize what this means, right? And again, I would totally spend time on that if we had the time, but we don't. So it's hard to work with, and that's unfortunate. The other side of that is it's also really important. Differentiability is something we're going to need to be able to establish. Differentiability, confirming differentiability sometimes is the difference between getting a right answer and getting a bunch of garbage that you didn't even realize was garbage. It's really important, right? So that's a problem. We're going to have to figure out how to deal with that. How are we going to be able to conclude differentiability without having to refer to the definition of differentiability? And there's a great answer to that question coming up momentarily. Real quick before we go on, there are a couple of details that you'll notice here are not in the optional section. I just want to point out here that if I kind of put parentheses around that and make this a plus, because of course that retains it actually being a minus because of the parentheses. That what that does, that is why this is the linear approximation. So that's where that formula on the right comes from. On the other hand, I could move the parentheses around in a different way, right? We could put the parentheses like that and like this. And this is another really nice way to think of this numerator. Instead of viewing this as actual value of the function minus estimated value of the function, you can view it as, actual change in the value of the function minus estimated change in the value of the function. So it's a different way of thinking about it. The reason I point this out is that these two terms, increment and differential, are going to come up in the rest of this course, and so I do need to have those terms established. So increment is a pretty natural term. It just literally says, how much the function actually changed. Right? That's what we're interested in. The word differential, commonly misunderstood term. A differential is a linear estimate of an increment. Right? So that's another thing that we need to keep in mind. We're going to use the term differential a lot, and when you're talking about the output value of a function, differential means the linear estimate of the change. Okay. Moving along. So here's how we're going to address that nasty little problem of differentiability. So in practice, without having to deal with that scary definition, look, I just need to know. I've got a function here. I just need to know, is it differentiable? Because I need to use theorems that require it to be differentiable. How do I know it's differentiable without dealing with ugliness? And wonderful little tool for that is this idea of continuous differentiability. Continuous differentiability is super easy to define. It's super easy to check. All you got to do is compute the partials world's easiest derivatives, right? Compute all of its partials, confirm that they exist. Most of the time, right, that's an eyeball glance. Most of the time you just look and be like, yep, here's the formula. Perfectly well defined, no explosions, no divide by zero, no natural log of a negative, right? Everything just works. And just establish that they're continuous. And so a theorem that y'all may recall from single variable calculus and that also holds in multivariable is that there is an enormous collection of known, already established continuous functions. And not only those functions, but their sums, their products, their quotients when the denominator isn't zero, basically, their compositions, basically anything that you can do with known, established, continuous functions are also continuous. And so in the great majority of cases, it's eyeball glance easy to establish that a function's continuous. You just, this is the sum of continuous functions. Done. Okay. So easy to check that a function is continuously differentiable, and wonderfully, if a function is continuously differentiable at a glance, this theorem says we immediately get to conclude that it's differentiable, right? We get to bypass all of the ugliness on the previous page, that nasty definition about vanishing relative error. That is not our problem. Easy to check it's continuously differentiable. Boom, done, differentiable. Go about your business. Everybody happy? All right. All righty. So, lovely idea. Now, real quick, related note, reasonable question to ask in relation to this would be, why don't we just define continuously differentiable to be differentiable? Right? So why have the distinction? And the answer is that this is a good news, bad news thing, but not every differentiable function is continuously differentiable. There are weird, anomalous little counterexamples of functions that are differentiable but not continuously differentiable. So if we were to just kind of throw away the hard definition and just ignore that ugliness, then we would be skipping out on a true statement, right? We would be missing conclusions that are important sometimes, and so we have to keep them as distinct concepts because they do talk about different sets of functions. But in practice, day in and day out, if you want to know a function's differentiable, check that it's continuously differentiable, conclude that it's differentiable. So case in point, let's look at this example here. If you find, for example, on a homework question or an exam question or something like that, hey, here's a function, is it differentiable? How would you conclude that this is differentiable? Well, it's very easy to compute the partials. It's fairly obvious at a glance that those partials are going to be polynomials. Polynomials we know to be continuous. Continuous partials is the definition of continuous differentiability. And the theorem above then tells us that that means that function's differentiable. Right, so it's a pretty immediate little connect the dots. You see how easy that is, nothing to it. Do make sure, please, when you write up one of these arguments, you do have to actually, doff the cap to all of the relevant points here. Very often, I see the following on tests sometimes, that students will say, all the partials are polynomials, and therefore the function's differentiable. And okay, but there are reasons. There are important details that just kind of got swept under the rug in such a response, right? The fact that it's differentiable is because of continuous differentiability. That's important. You really can't just gloss over that. You need to recognize that the continuous differentiability is what makes that work. And furthermore, the fact that the partials are polynomials is not what gives you that. It's the fact that the partials are continuous that gives us that continuous differentiability. So this continuity is, again, that's an important part of the argument. You can't leave that out. Right? So please do be careful. Please think carefully about, okay, what are the important players in the argument that I'm making, and then make sure that you recognize and document those important players in your argument. Okay. All right. Another useful fact, and this is a pretty easy read, I think. By the way, this uses what we call the contrapositive. I think this is a really nice construction. The contrapositive says that if you have the implication P implies Q, the contrapositive says, well, if Q is not true, then P couldn't possibly be true. Right? It's a very natural little logical tool called the contrapositive. Very nice. And that's ultimately what's being used here. The fact that differentiability implies continuity, if you take the contrapositive of that, gives you a useful tool. If you can confirm that a function is not continuous, then you don't need to try to prove that function's differentiable, because it's not. You instantly know from lack of continuity that function's not differentiable. Okay. All right, and y'all can look at this example if you like. I think it's a pretty easy read. You can look at that picture. You can see it's clearly discontinuous and therefore not differentiable. Okay, yeah, we're moving along. So just a shuffle of what we've already written down. So we've already written down our linear approximation as this. And keep in mind, this is our fully general linear approximation. Multiple input variables, multiple output variables, namely vector-valued output. This is as general as a what I might call a Euclidean function can get. As many inputs as you want, as many outputs as you want. And here's our linear approximation we already talked about. So now just to kind of shuffle terms around a little bit, in some sense the whole point of one of the points anyway of a linear approximation is that at the point A, F and L agree. So I can rewrite it like that. Then subtract that term over to the other side. And check it out. I mean, no big deal here, but what I've got as a result is that the left-hand side is the output differential. There's that term again. Right? Keep in mind the output differential is the linear estimate of the change in the value of the function. So looking at the change in the linear estimate, well, yeah, that's what that is. And then look at what df does. df acts on the input differential. Right? How much did the input vector change? So, in an amazingly sort of pithy result, what we have is that the df matrix is the thing that you multiply by input changes to get output changes. And I think it's wonderfully pithy. So dr is our input change. Df then is our linear estimate of the output change. So this thing called df turns input changes into output changes. This thing called df is the most general object that meets our rule for what deserves to use the term derivative. Right? A relationship between input changes and output changes. So df is the most general, what I think you could reasonably call derivative of any of these kinds of functions. And so very important terminology to be aware of. This df is called, wrong color. Df is called the derivative. Sometimes it's clarified as the derivative matrix, and of course matrices are always linear transformations. So sometimes people say the derivative transformation. Fine. Any of those terms are fine. But the point is that this is what a derivative is. It throws students for a loop a little bit sometimes, because you're probably accustomed, right, back in single variable calculus, to thinking of a derivative as being a number. It's the slope of the tangent line, right? I mean, it's a number that represents something important for a single variable function. Well, you change the kind of functions, you change what kind of critter a derivative is. A derivative is no longer a number. A derivative is a matrix in this sense. Let me pause there for a second. There's something to kind of get used to there. Does anybody have any questions about that? Weird, isn't it? Okay. All right. By the way, also sometimes called the Jacobian matrix, and so with that in mind, sometimes written as JF. So be on the lookout for that sort of thing. Yeah. All right, so here's just kind of a picture representing what we just talked about. The derivative is the thing that turns input changes, namely, if you were to look at your domain on the left and say, well, I'm starting at the point A, but then I'm going to move by some amount, some differential amount, dr. Then df turns that into the output change, df, the output differential, that is, our linear estimate of the output change. So a nice way to think about the derivative matrix. Turns input changes into output changes. Now here's a tweak of that. Pretty similar idea. Take that and just divide by dt on both sides of the equation. And conveniently, now check it out. Now the left-hand side is no longer a discrete change. Now it is literally a derivative. And y'all may recall, and we're gonna talk about this more in a couple minutes, but the derivative of position is naturally understood as a velocity, right? A direction and a magnitude of the motion. So that's input velocity. Again, also represented by a vector. And then now look at on the on the left-hand side, the output side, what we get is, again, a velocity. It's a derivative of a vector value in the target. So again, the derivative is the thing that turns now input velocities into output velocities. And if you think about it, velocities are kind of changes. They're rates of change, but they still represent changes. So this is a tweak on the idea of input changes to output changes. Okay. Here's what I like about this point of view. With this point of view, I don't have to put in the little asterisk of, well, we're doing linear estimates, and so this is the output differentials, an approximation, and the reality is going to be a little bit different. You don't have to put the little disclaimer in there because we're talking about derivatives, because we're talking about instantaneous velocities. This is true as written. This df matrix turns input velocities into output velocities. Full stop. It's a little bit cleaner in that sense, right? And so I find that appealing myself. Okay. All right. Moving along. Now, we kind of leapfrogged over the, let me go a couple pages back. Oops. Oh, a little bit further. We kind of leapfrogged over this formula right here. Erase the... when you have a real valued multivariable function, right? Remember that the idea is that you can use dot product with the gradient to produce this form of the linear approximation. So this is not, as written, this is not derivative matrix times input differential. It's a vector dot the input differential. So here's the thing, though. If you look at what the df matrix would be for such a function, right? And let me give myself some more space here. What would be the DF matrix for this function? Well, remember, rows correspond to outputs. This is a real valued function. There is only one output. And columns correspond to input variables. So this would be the partial of g with respect to x1. Next element in this row, partial of g with respect to x2, etc., down to partial of g with respect to xn. So that's what the derivative matrix is. And, well, check it out. It's kind of all the same numbers. Right? It's not that different. And in fact, when you have a single row matrix multiplied by a vector, keep in mind that computationally is the same as just dotting with the associated vector, which is the gradient in this case. Right? So, in fact, it's not a different calculation at all. So now I went ahead and wrote it here. Oh gosh, I got to scroll all the way back. Oh man, we covered a lot of ground there. Here we go. It really is morally the same thing. This dot product with the gradient is morally the same as multiplying by the derivative matrix. So dot product with the gradient, multiplying by the derivative matrix, and it's all the same arithmetic. Okay. All right, so think of this as just, this business with using the gradient as a way to write the linear approximation. Think of this as a tool. Think of this as an alternative notation for what is morally the same thing. And yes, in this special case of multivariable but real valued, yes, it can be a convenient alternative notation, but it's just an alternative notation. Okay. All right. Okay. More stuff that I'm going to let y'all read through because, again, tough choices and more difficult material later on, blah, blah, blah. Y'all have heard that a million times. So there is a little bit of a fine distinction being made here in this lead-in statement, and I just want to make clear what we're talking about here because this is subtle. Ultimately, the statement being made here is that derivatives are linear, and there's a temptation to say, well, we already knew that because that's what a derivative is. It's a matrix, and matrices are linear. Yeah. Okay, but that's not what we're saying here. We're saying something importantly different. Yes, the derivative matrix, the result of differentiating a vector-valued multivariable function, yes, that is a linear transformation. True. And, inputs to outputs. Yes, the DF matrix is a linear function from purple to blue. Yeah, absolutely. That's not what we're talking about here. What we're talking about here is a different statement. We're talking about D. D is what turns a function into a derivative matrix. So the thing that turns green into blue here, that's what we're talking about with this statement. Not the result of differentiation, but the act of differentiation. The act of taking a derivative turns a function into a matrix. That's what I'm saying is linear. Right? So notice the way we've written this down algebraically is that differentiation, D, right, takes a linear combination of functions, linear combination with coefficients A and B, and gives you that same linear combination of the resulting matrices. Right, so this is in this context for that, weird linear transformation D, this is what it means to say that when you put a linear combination in, you get a linear combination out. This is what it means to say that D is linear. So it's not a statement about linear combinations of vectors in Rn. the statement about linear combination of functions. Okay, so make sure to be careful with that distinction, and there's an example to follow. Again, that's something I'm going to let y'all read. I think this is a pretty straight read. Just some computations, plug and chug, and note, confirm that, yep, sure enough, it works as it's supposed to. Okay, and then there's a reference in here to some stuff in the book. These are, again, very straight read. You don't need me to walk you through this, but do make sure that you notice the product rule and the quotient rule that applies in some cases, right? You do have to be careful about when you can apply them, but nevertheless, it's a pretty straight read. Okay, all right. And then this page, another pretty straight read. Y'all can totally do this. This is just the observation that just like with single variable derivatives, you know how if you're doing single variable calculus, you take a derivative, you could then take a derivative of that derivative. All right. Well, you can do the same thing with partials. If you have a multivariable function of certain variables, and if you take a partial derivative of it, the result is something that you can take partial derivatives of, right? Just in the same way. You can take derivatives of derivatives. And now there's some resulting notations and awkwardnesses. And again, so make sure to read this stuff. I'm going to point to the awkward notation issue here, because this is really unfortunate. Both of these notations begin with a function f to which I first take a partial with respect to x, and then to that partial with respect to x, I'm then subsequently going to take the partial with respect, let me just be consistent here, the partial with respect to y, and notice the awkward little notational point here. The x is on the right with the Leibniz notation, but it's on the left with the subscript notation, and vice versa for the y's. It's so annoying, but this is the way it is, right? That's unavoidable. I mean, surely we have to keep that and this in the same order. I mean, it would be insane to not have those in the same order. And then likewise, surely we have to keep these in the same order. My gosh, I'd lose my mind if those weren't in the same order, right? So, well, then, this is what we have to deal with as a result. So do be careful about the order that you write those down in. Now, that said, good news. It turns out, in many cases, it actually kind of doesn't matter. In many cases, the order that you take the partials will always give you the same result. This is true in most cases. This is true in this case, for example. You notice that you do the x partial of the y partial or the y partial of the x partial, whichever way you do it, 15x to the fourth y squared. Same. Nice. Right? And that's true most of the time in some sense. Specifically, it's true whenever the function in question is what we call CK. CK is a convenient way of saying that not only is the function continuous, but the partial derivatives are continuous, and the second partials are continuous all the way up through and including the kth order partials. So there's a lot of partial derivatives that have to be computed to confirm that's true, but again, beautifully, it's been done. And so, for example, it is already well established that all polynomials are CK. In fact, all polynomials are C infinity. Take as many partials as you want. You'll always get agreement when you just reorder the ordering of the derivatives. So lots and lots of functions already known to have this property, and therefore most of the functions that you're going to deal with in practice, day in and day out, reorder the derivatives however you like. Okay, and that's a pretty good place to call it. We'll draw the line right there. See y'all later. See you on Wednesday. Have a good one.